Okay, welcome back. We continue with these properties of determinants and these very numerous example types, some of which are labeled exam style examples, like the last one, letters in the matrix. What are you supposed to do? Well, you want to bring these other uglier matrices to look like the original comparatively not so bad matrix using row operations. The next one's different. The next one says that you're asked for the determinant of A, where A has letters and numbers in the matrix, and it tells you what the determinants of some other letters are. Determinants of FGH, JKL, NOP is equal to 5, and the determinant of EGH, IKL, MOP, like where are these coming from? And what you have to do is you have to think about how can you combine the information that's given below, how can you use that information to construct the determinant that's asked for. You can't use a secret method because number one, it's not 3 by 3. Number two, you don't have enough data to use a secret method. There's letters in the way. You can't use row operations because you can't convert a 3 by 3 into a 4 by 4. There's no row of zeros as far as we can tell, no column of zeros, no duplicate rows or duplicate columns, not triangular, not diagonal. Like we're out of tricks. What does that leave? If all the tricks have been removed, we can't use any of our shortcuts. There's only one thing left. Our worst enemy is left. Cofactor expansion. We have to do cofactor expansion. So here we go. Cofactor expansion. We're going to expand along column 1. All of our tricks and shortcuts are powerless. Must do cofactor expansion along the dreaded row 1. We can't even be strategic. We can't even pick a good row. We have to do the first row. So the determinant of A, according to the cofactor expansion, is A11 times C11 plus A12 times C12 plus A13 times C13 plus A14 times C14. Since it's a 4 by 4 matrix, we're going to have 4 of those pieces. Now, what is A11? It's a 1, 1 entry of the matrix A, so it's 2. What is C11? C11 is negative 1 to the 1 plus 1. Oh, I gotta write these smaller so they'll line up. I'm gonna force them to line up with the plus signs. So A11 is 2, and then C11 is negative 1 to the power 1 plus 1 times. It is foolishness to try to get them to line up. I cannot do this. So times the determinant of the submatrix A11. That's what a cofactor is. Plus the next entry, A12 is 4 times negative 1 to the 1 plus 2 times the determinant of the submatrix A12 plus negative 1, that's the A13 entry, times negative 1 to the 1 plus 3 times the determinant of the submatrix A13, and then plus 3 times negative 1 to the 1 plus 4 times the determinant of the submatrix A14. I couldn't even get it all in one line. Okay, so I have a 2 multiplied by a 1, negative 1 to the power of 2 is just 1, times the determinant of that submatrix that I get when I remove row 1 and column 1. That's the submatrix A11, so it'll be FGH, JKL, NOP, plus I have 4 times negative 1 times the determinant of the submatrix A12. So for A12, I remove row 1, I remove column 2, and what I'm left with is EGH IKL MOP. And you're looking up top, you're looking above at the data that we have, and you're getting excited because we have all those things. Plus, or maybe you're not getting excited. Maybe it's just me. -1 multiplied by +1 times the determinant of the submatrix. And I'm going to just shift it over. Now we want the A13 submatrix. So if we remove column 3 this time. So we got EFH. Oh. IJL MNP. And we have one more. We have +3 times -1 to the power 5, which is -1, times the determinant of the last submatrix. We get rid of the last column, first row, submatrix A14, EFG, IJK, MNO. All right, and now we can start plugging in information. We have 2 times that determinant, which is 5, minus 4 times that determinant, which is 3, and then minus the determinant of the EF, which is 6, and then -3 times the determinant of the EFG, which is -2. And we can simplify. So 10 minus 12 minus 6 plus 6, we get -2. And I really hope that's the answer. If I have any mistakes, say something. Email me. Say something in the forums. Don't let the mistakes live too long. I'll correct them if there are errors. So it's a very horrible calculation. It's mechanical, but it's horrible. What else is there? Well, we saw that we can use row operations to simplify a matrix. And then in the simplified matrix, take the determinant, being able to subsequently, to then after simplifying it, use one of the shortcuts. What we're going to examine next is how do matrix operations just modify the determinant. So what's the relationship between the determinant of A and the determinant of A inverse? Is there a relationship? What happens if you multiply 2 matrices together? Or, sorry, scalar multiplication. What happens if you multiply a matrix by a constant? We've already seen this. We already saw this as kind of a shortcut figured out by doing a few experiments, but we'll formally state it inside this section. What about adding 2 matrices together? Is there a shortcut there? Is there a relationship between A and B, determinant of A, determinant of B, and determinant of A plus B, or A minus B? Like, is there some relationship we can exploit, or are we flat out of luck? What about multiplication? What about multiplying 2 matrices like A times B? Let's say I have the determinant of A and I have the determinant of B. If I want the determinant of A multiplied by B, do I have to create that from scratch? Or is there some formula that I can use that will use the existing data as a shortcut? So we already did the experiment of multiplying a matrix by a scalar and taking the determinant and seeing what happens. And what happens is, if for every row that we have, that scalar multiplies by the determinant for each of those rows. So if you have 2 rows, the scalar hits the determinant twice. If you have 3 rows, the scalar hits the determinant 3 times, and so on. So just to do one more experiment along those lines, the determinant of A, with A given here, determinant of A is 1 times 10 minus 1 times 1. So 10 minus 1, which is 9. For this one, determinant of A, or 3A, you gotta be careful when I write, determinant of 3A is 3 times 30 minus 3 times 3. So 90 minus 9, which is 81. And the relationship between this and this is multiplied by 3 multiplied by 3 once for each row. So 9 times 3 times 3, 9 times 9, 81. So you have to know the size of the matrix. You have to know how many rows or how many columns the matrix has in order to use this type of a shortcut. So it's stated formally that if A is a square matrix of order n, so for determinants have to be square anyway, if it's of order n means it has n rows and n columns, and C is any scalar, then the determinant of C times A will be C to the power of n multiplied by the determinant of A. So one value of C is coming out for each row of A. So C times C times C times C, n times for however many rows the matrix has. And the way that we can visualize this is thinking about our factoring method. When we multiply an entire matrix by a scalar, that's multiplying each element, which is equivalent to multiplying each row by that scalar. We can then factor that scalar, that constant, out of row 1, factor it out of row 2, factor it out of row 3, factor it out of row 4, factor it out of each row. We'll have C to the power of n in front multiplied by the determinant of the matrix without the constant. So that's why this method is the method. It has to do with that row operation. It's a shortcut predicated on that. So we were a little bit ahead of ourselves when we were using it, but now we're fully justified in using it. Okay, so an example, we're asked to find the determinant of the negative of A if the determinant of A is 5 and A is a 3 by 3 matrix. So the determinant of negative A is going to be, determinant of negative A is going to be, I'm going to take the negative 1 out 3 times, negative 1 to the power of 3 times the determinant of A. So we factor out a negative 1 from each row. So that's negative 1 times the determinant of A, which is 5. We get negative 5 as our answer. Okay, the next one. What if A is 4 by 4 instead of 3 by 3? What's the determinant of negative A? So determinant of negative A is equal to negative 1 to the power of 4 times the determinant of A, which is positive 1 times 5, which is positive 5. So we change the size of the matrix and it changes the result. Okay, and then the last one here, it's a different modification of A. We want the determinant of 3 times B, 3B, if the determinant of B is negative 1 and B is 2 by 2. So this is going to be determinant of 3B, not D, B, 3B, is equal to 3 to the power of 2 times the determinant of B. So we took a 3 out of each row, factor out a 3 from each row. So it'll be 9 times -1, which is -9. Pretty nifty. What about multiplication of two matrices, A and B? Maybe it's painful to multiply the matrices. Maybe one of them 7 by 7, the other one's 7 by 7. We know what the determinant of the first one is. We know what the determinant of the second one is. Maybe they're both triangular. One's upper triangular, one's lower triangular. We really don't want to multiply them together. We're going to have 7 dot products. Each of them is a dot product between two 7-element vectors, a column vector and a row vector. I mean, we're probably going to make a mistake if we do it, because there's so many multiplications and additions to do. If there's a shortcut, I mean, it would be nice to be able to use. I'm not going to prove this. It is something that you can prove if you're desperate to prove it. If you really, really want to, you can find proofs. You can find books full of proofs of things like this. But it's not part of the, I mean, I put a few proofs in, but it's really not part of the course to do too many proofs. So just trust me. That the determinant of a product of matrices, the determinant of A times B, is always going to be equal to the determinant of A multiplied by the determinant of B. And depending on what the matrices are, this can be a gigantic time saver. For example, we want the matrices A, B, and C. We want the determinant of that product, A times B times C. I mean, they're 2 by 2 matrices. It isn't that hard to multiply them. But I'll leave that to you. If you want, multiply A times B times C, and then take the determinant of the resulting 2 by 2 matrix and compare to the amount of work it takes to find each determinant separately and use the property. So determinant of A is equal to 3 times 5, 15, minus 7 times 2, 14, which is 1. Determinant of B is equal to -1 times 4, -4, minus 3 times 6, -18, so -22. The determinant of C is equal to 12 minus 12. So 6 times 2, 12, minus -4 times -3. So -4 times -3 is positive 12. 12 minus 12, 0. Thus, determinant of A, B, C is equal to determinant of A times the determinant of B times the determinant of C, which is going to be 1 -22 times 0, which is a big, juicy 0. We do not need to multiply the matrices together. We barely have to multiply those numbers together. So compare it to multiplying them out, though. If you want to see the time savings to theory, like, well, what good is theory? It's about efficiency. Understanding theory allows you to make breakthroughs, allows you to make orders of magnitude improvements, not little like 1% improvements, but factors of 10 improvements to things. How about this set of matrices determine A times B, that determinant? They're not that bad to multiply. They're 3 by 3s. So you're going to have, let's see, row 1, row 2, so you're going to have 9 dot products to do. Well, I think I misspoke when I said 7 by 7. You're going to have 49 dot products to do for that one. Sorry about that. Here you have 9 dot products to do for this. Each of them's not bad. They're small. But it's not as easy as just noticing that each of these matrices is triangular. So each has a beautiful determinant. So triangular. This one's upper triangular. The next one's lower triangular. It doesn't really matter if we label them upper or lower right now, but I'll label them anyway. So the determinant of A is equal to 1 times -2 times 10, which is -20. And the determinant of B is 2 times -1 times 2, which is -4. And I will use the property, the determinant of A times B is equal to determinant of A times the determinant of B, which is going to be those two numbers multiplied together. -20 times -4, which is 80. Okay, and we'll continue in the next video.